Hello everyone, welcome for this lecture. Today we are going to discuss numericals on AC circuits. So till now what we have done is we have solved numericals on DC circuits, that is source transformation. We have studied on DC circuits and we have applied source shifting and we have applied star to delta transformation and loop analysis, mesh node analysis, super mesh, super node. So all these techniques we have applied for DC circuits. So today we are going to apply for all those techniques to the AC circuits. What is the difference between AC circuits and DC circuits? Remember only one thing, that in a DC circuits we have only resistors, okay, and along with that polarities also, right? So here in the AC circuits we will be dealing with the impedance instead of resistance. That impedance may be resistance, inductive reactance or capacitive reactance. Okay, so now let's see how this AC circuits. Okay, so will be main thing, we will be dealing with the Z. Okay, Z will be equal to R plus J X. Okay, if we have a inductance, inductive reactance, that is XL, which can be calculated by J omega L. Okay, so this if we have, then we can say it is R plus J XL. Suppose if we have a capacitor, then it will be XC, right? So this one will be Z can be written as Z is equal to R minus J XC, where XC can be calculated as 1 divided by J omega C. Okay, like this. And one more thing is, when you are dealing with the AC circuits, we will be discussing on, means we will come across, so A at an angle B form and A plus JB forms any values of those, because those are complex numbers, right? So those can be represented in these two forms. So A at an angle B is your polar form, okay, and A plus JB is the another form, that is the rectangular form. Okay, rectangular form. Okay, so these two are forms. So about this we have discussed in earlier classes, that is in a previous semester. So there we have come across it. Okay, so today we'll discuss about we are going to apply all these techniques which you have studied earlier on this circuits. Okay, so before that, let's see what is that impedance R plus J XL. Once glance this all, if the circuit consists of pure resistance, your impedance will be R only. Okay, it is nothing but your DC circuits. Then if the circuit consists of pure inductance, it will be Z is equal to JXL, right? If it consists of pure capacitance, then it will be minus JXC. Okay, and then if you say why it is so, then we can say 1 divided by J omega C. 1 divided by J can be written as minus J. Okay, so then if your circuit consists of RL, then impedance will be R plus JXL. If it is RC, then it can be taken as R minus JXC. If your circuit consists of RLC, then it will be R plus JXL minus JXC. Okay, as we said, we will come across these two, polar form and rectangular form. You have to remember this, and this can be converted into from polar form to rectangular form and rectangular form to polar form, vice versa. Okay, that can be done by your calculator. Okay, let's take a simple example of this, how to deal with this AC circuits. Remember, this is whatever the techniques and methods we have to apply, how we used to apply for a DC, same technique we are going to apply. Only difference is these values are in the form of polar, or it may be rectangular form. Okay, so these forms we have to consider, okay, throughout the calculation, and we have to give a result in this form only. Okay, that is the only difference. Other than that, applying method, what are the techniques are there, those remains the same. Applying whatever the procedure is there, that remains same. Let's see. So this, they have asked us to calculate, find the I current I in the circuit. Where is that I? Here it is. Okay, so if you observe this circuit, remember they have given one AC voltage source and then there are three impedances. How these three impedances are connected in series? So what we can do is we can add all these resistances, take a equivalent resistance, then your entire circuit will become single source with one impedance like this. Then this is a I. As we know, this is total impedance. Okay, to calculate I, you can apply simple Ohm's law also, that is V divided by Z. Okay, V divided by Z. So since you know V as well as Z, so then you simplify it, you get a result of that. Okay, so whenever you are operating in a calci, remember your calci should be in complex mode. Okay, in a complex mode, not in a compound mode which you use to operate regularly. Okay, it should be in a complex mode, right? So in this circuit, we have to calculate I is equal to V by Z. So V, though they have given, that is 100 at an angle 0 degree volt. Okay, now so that Z impedance, there are three impedances, those are all connected in series. Let's calculate its equivalent series impedance, that is just addition of all three. Okay, series 5 at an angle 50 plus 4 at an angle 60 plus 10 at an angle minus 20. Be careful about while writing this, always you prefer to take these values in terms of within a bracket. Okay, so that gives you accurate results. So Z is equal to, if you add these things, you get 14.61 plus 3.87 J. Okay, total impedance, if you are, this is your polar form, sorry, this is your rectangular form. Now let's convert this into a polar form. This is your polar form. Okay, next 15.1 at an angle 14.85 ohms. Total Z we have got. So V you know, Z you know. Calculate I is equal to V divided by Z. V is 100 at an angle 0 divided by 15.1, that is Z, 15.1 at an angle 14.85 ohms. So if you form this, you will get as a rectangular form, and this is your polar form. Okay, so this is I is equal to 6.615 at an angle minus 14.85 ampere is your polar form. Okay, current, anyone you can express, either polar or rectangular form. Prefer to express in polar form. Okay, so next we'll take another example. So what I said is we have to apply all the possible, means all the techniques we can apply for AC circuits. Now we have applied Ohm's law. Let's see the conversion, that is the source transformation from voltage source to current source and current source to voltage source. See, they have given us they have said that entire circuit can be represented by current source. They have asked us to find out the equivalent current source for the given circuit. So what they have given, it is a voltage source and that is the impedance. So now we need to convert. While converting it, we know the part that with the voltage source impedance will be in series and current source impedance will be in parallel. Okay, this you know to draw, right? Once you have drawn, what you have to do is impedance remains same, that is Z, that is 5 plus 5 J remains the same. What about I will be equal to Vs, whatever they have given, voltage divided by Z. Okay, Vs divided by Z, if you do, that is 10 at an angle 0. Okay, voltage divided by 5 plus 5J, take it, it is equal to 1 minus 1J, sorry, it should be a rectangular. Okay, this is your rectangular, and then convert that into a polar form, you get 1.414 at an angle minus 45 degree. Okay, which is polar form. Okay, anyone you can replace, but only thing is prefer to represent in polar form. Okay, so everywhere I have written, I'm sorry for that. Okay, next, similarly same methods, convert the circuit into voltage source. So they have given in the form of current source, convert that into a voltage source. Representation is this: voltage source along with that impedance in series, and impedance will be remains the same, that is 3 plus 4J, it remains same. Only V has to calculate. V is equal to I into Z. I is 10 at an angle minus 30 degree, okay, take it in a bracket, into one more bracket you take, in that 3 plus 4j you do. The once you multiply, you get in a rectangular form. Another one you get in form of polar. Okay, 50 at an angle 23.13 volts. Right? This is the source transformation technique. So now let's see. We will find out the other one. That is, they have asked us to calculate, use the source transformation technique, find current through 10 ohm resistance. Okay. So where is the 10 ohm resistance? Identify where is the 10 ohm resistance. Here it is, a 10 ohm resistance. So then don't alter this part. Okay, it remains the same. Then what we can do, they have not mentioned by using what, but just they have said so use the source transformation technique. So what we can do, there are two possibilities to do. Okay, this one is a voltage source, this one is a current source. You can convert this into a current source and then you can deal. Only thing is, we are very familiar with the KVL, okay, that is a mesh analysis, instead of going for a KCL, okay, that is your node analysis. So prefer, let it be as it is, this voltage source, that is 100 at an angle 0 and 5J. Then what we can do is convert this current source into a voltage source. Once you are taking a voltage source, one voltage source comes in series with this part, and this impedance will be remains the same, that is minus 5j in series with the source. Okay, and this 10 ohm as it is, right? So convert this, V is equal to what? I into Z. So I is how much? I is 10 at an angle 90 degree. Okay, take in a bracket. Okay, take in a bracket. Multiply with Z, that is minus 5j. Okay, when you multiply this, you get 50 at an angle 0 volts. Okay, 50 at an angle 0 volts, and then minus 5j impedance will be remains there in series with that. So now a single loop we have got, we can easily apply KVL. Okay, before that what we can do is impedances, say, observe, this is plus 5j, this is minus 5j, so this will be 0, right? So this impedance will not be, means it goes to 0. So then you have a voltage source, that is one voltage source is, you can add. So one voltage source is 100 at an angle 0, another one is 50 at an angle 0. When you add these two, you get 150 at an angle 0 volts. Okay, that you can take. Voltage source you have got, impedance to 0. Then what about this resistance? It will be 10 ohm. Now we can apply KVL, or you can directly write I is equal to it, because there is this term is not there, means only voltage source and resistance is there. V by R you can write. So V by R is nothing but your 150 by 10, which is nothing but 15 amperes. Okay, so this is how we can deal with this. Like I can apply KVL, or you can directly apply Ohm's law. Okay, next type of numerical we'll see. We'll apply this star delta technique on this AC circuit. They have given that this, for the circuit shown below, this has to be converted into a delta circuit, means delta network. Okay, obtain equivalent delta network for the circuit shown below. So whatever they have given this circuit, we have to get it a delta connected circuit. So observe this between A and B. Okay, let's take this one as a C. Okay, between that we can take as a C term. So observe between A, B and C, what are the terms? You can observe this. This is no, meaning of this one is jumped wire. Okay, which is not connected to this wire. Okay, now you can observe between A, B and C, there are two, okay, there are two star connected network. One is 10 ohm and 5 ohm resistance. Okay, this is one. Another one is between those three terminals only. One is 10J and 5J ohm resistance, impedances. Okay, so those two, there are two star connected circuit we have. Take them separate. Okay, convert them into a delta. each one, let's convert them into a delta. This is one circuit, 10 ohm, 10 ohm, 5 ohm resistance, pure resistance, and another one circuit we have 10j, 10j, 5j impedances circuit. So there are two independent star connected circuits. Let's convert each one into a delta. Okay, each one into a delta, and then replace, like, place this is one between ABC and this one, combine those two, you will get, once you combine, you get this circuit. Once you combine this, so between A, B and C terminal, these two 40 ohm resistance and 40j impedance, these two are in parallel, these two are in parallel, and these two are in parallel. Take a parallel combination, parallel formula, that is to calculate between this, that is RAB will be, or ZAB will be equal to what? 40j into 40 divided by 40j plus 40. Okay, if you do this, you get a ZAB. Okay, and similarly you can calculate ZAC, and then you can calculate ZBC or CB. Okay, like this you can do, and you can represent, right? Let's do this. Let's take first one. Let's take a first star connected network, that is 10 ohm, 10 ohm and 5 ohm. As we know, this formulas are, to calculate RAB, formula will be RA plus RB plus RARB divided by RC. Okay, I hope you remember this formula, right? RA plus RB plus RARB divided by RC. Once you have done this, you can substitute all the values. RA is 10, okay, plus RB is 10, right, plus 10 plus 10 plus 10 into 10 divided by 5. Okay, 5 ones are 5 twos are, so 20. 2 tens are 20. Then 20 plus 10 plus 10 is a 40. Okay, so this term will be RAB is a 40. Similarly, you can calculate RAC, which is RAC is equal to RA plus RC plus RARC divided by RB. Okay, calculate it. RA is a 10, RA is 10, and RC is a 5 plus RARC, that is 10 into 5 divided by RB is 10. So 10 goes, the 5 remains, 5 plus 5 is 10, 10 plus 10 is 20. So RAC is 20. Okay, similarly we can calculate RBC. So similarly we can calculate RBC, which is equal to RB plus RC plus RB into RC divided by RA. Substitute all the values. RB is 10 plus RC is 5 plus 10 into 5. Okay, these two only, RB into RC. So 10 into 5 divided by RA. RA is 10. So 10 goes, gets cancelled. 5 plus 5 plus 10, which is 20. So RBC is also 20. Similarly, you can calculate this star into delta form. Okay, to calculate that, it remains the same. I have just substituted here as the resistances. Here you have to substitute in terms of impedances. That's it. RAB, here instead of RAB, it will be ZAB. Okay, ZAB will be equal to ZA plus ZB plus ZA ZB divided by ZC. Okay, what is the ZA value? 10J plus, what about ZB value? 10J plus 10J into 10J divided by 5J. 1J get cancelled, 5 ones are 5 twos are. So it is 10 twos are 20J, 20J plus 10J plus 10J, which is 40J. Okay, similarly we can calculate this AC and BC. So once you calculate these two, we can place there. It is A, B and C. So first delta is of pure resistance, second delta is of impedance. Okay, once you have connected it, so observe 40J and 40, 20J and 20, this 20J and 20 are in parallel. Okay, these two are in parallel, these two are in parallel, and these two parallel. Take that parallel combination impedances, which is ZAB. Okay, ZAB can be written as between these two, that is 40J into 40 divided by 40J plus 40. If you do this, we get ZAB, which is 20 plus 20J. Okay, similarly you can calculate between AC, that is ZAC, which is 10 plus 10J, right? And then between BC you can calculate, which is 10 plus 10J BC. Okay, right? Now this can be represented in this form. It is A, it is B, and it is C. Those all are in delta connected. Okay.